Swayam Prabha. Digital India. Educated India.
Let us move on to the next problem. So here the product A and B that are formed in the following sequence of reactions. The starting material is given. It is an alkene. The alkene is treated with the selenium dioxide in the presence of dioxin and heating. That leads to the intermediate A, and this intermediate is further reacted with aqueous sodium cyanide followed by MnO2 oxidation. So these two reactions are done sequentially. And the third one is the reaction with the dimethylamine in the presence of isopropanol to give the final product B. So we have to identify what is A and B. This question was asked in June 2014. So basically when we look at the selenium dioxide is generally used for the allylic oxidation. So if you look at all the substrate, the combinations 1, 2, 3, 4, all of them have the allylic aldehydic group that is present here. So that means all combinations are possible. Now only we have to look out whether we can rule out what could be the product that will not form in this one. So in the second step, if you look at, we have a sodium cyanide reaction and MnO2 oxidation. So sodium cyanide reaction may probably convert the aldehydic into the cyanohydrine. MnO2 will oxidize that cyanohydrine into acyl cyanide. And finally we have the dimethylamine that is undergoing reaction. So the cyanide group will be converted into the dimethylamide. So that is probably the reaction we are actually going to look at. So that means if we look at the 4 product, so we have a ester that is formed here. So since the sodium cyanide is added, so our product has to have the nitrogen atom, and in this one we don't have a nitrogen atom, so we can completely rule out. 3 is not the probable one. And if you look at 2 also has only the all oxygens, no nitrogen is there. So that means we can also rule out 2 is also not the product. Now we have to only look out at 1 and 4 are the 2 probable product. And if you look at 1 and 4, the difference is whether the aldehydic group is cis to in the double bond or it is trans. That is the only thing we will have to actually look out. Based on that, we can say what is going to be the final product. So let us move on to how to solve this problem. So the starting material is undergoing reaction with the selenium dioxide. So this selenium dioxide reaction is a little bit lengthy reaction. We are going to look at how the reaction actually proceeds, because we know it is an allylic oxidation, but how the allylic oxidation takes place, that's what we are going to see. So this reaction basically follows a Yin type reaction. That means a electrophilic selenium center is the crucial one which undergoes the reaction. Here we have a nucleophilic oxygen, another nucleophilic oxygen or electronegative oxygen. So the electronegative oxygen actually pulls the electron towards itself, making this center delta positive. So we have the electrophilic center that is present in this molecule. This is similar to carbon dioxide molecule. If you look at, oxygen pulls the electron towards itself, and the carbon is forming as a electrophilic center when CO2 undergoes a reaction. Similarly, selenium dioxide is also very similar to that. So the central selenium is now electrophilic in nature. We have a nucleophilic double bond. So obviously the nucleophilic site and the electrophilic site will react together, and oxygen, which is electronegative in nature, will pull the pi electron towards itself, so making it like a O minus ion. And this O minus ion, we have a hydrogen atom in the adjacent place. So this will simply abstract that hydrogen atom. So this is how we can actually understand how the reaction actually proceeds. So this follows a 2,3 sigmatropic shift that is happening here, that results in the formation of allyl selenic acid. So one of the oxygen pulls the hydrogen from this substrate and getting converted to the hydroxide. So if it is a carbon, we say it is a carboxylic acid. Since it is selenium, it is called the selenic acid. So we have a external double bond that is getting formed in the 2,3 sigmatropic shift. So this mechanism was actually proposed by Sharpless. So that is the reason I had given the name here. And this allyl selenic acid again undergoes one more 2,3 sigmatropic shift. So here again the shift of electrons are given here, how the bonds will be migrating. The oxygen will attack the olefinic carbon atom with the olefinic double bond shifting towards internally, and with the carbon selenium bond that is getting broken to give the selenite ester that is finally formed here. So that selenite ester now moves actually from the internal position to the terminal position, it is actually getting moved. So that is what is the major thing that is happening in this reaction. So this 2,3 sigmatropic shift moves the selenium from the internal place to the external one. And here when this shift takes place, this selenium ester can be further hydrolyzed to give the corresponding allylic alcohol, and this reaction actually gives the trans product. So that is the main thing we have to understand, and based on that we are going to predict what is going to be the product. So if you look at the R group and the allylic alcohol that is formed, these are trans to each other. So this reaction is a fully regio and stereospecific reaction, and here there are two consecutive pericyclic 2,3 sigmatropic shifts are taking place, and this reaction is overall reaction of conversion of an alkene to an allyl alcohol is called as Rayleigh oxidation reaction. So this reagent selenium dioxide is the important one that is involved in the Rayleigh oxidation reaction. So once the allyl alcohol is formed, what is going to be the next step? The next step is the oxidation under the reaction condition. It is getting converted to the corresponding aldehydic unit. So once the alpha beta unsaturated system is formed, the next reaction is reaction with aqueous sodium cyanide. So this basically undergoes a nucleophilic substitution reaction on the aldehydic carbon. So we end up with a cyanohydrin derivative that is formed. And this cyanohydrin derivative is further oxidized by manganese dioxide. MnO2 oxidizes the alcoholic unit to the carbonyl unit. So we end up with the acyl cyanide as the product, and this acyl cyanide further reacts with the dimethylamine in the presence of the solvent isopropanol. The presence of isopropanol, dimethylamine reacts with the cyanide unit to give the corresponding amide unit. So if we are going to see the product B, the product B is basically having this group and this group are basically in the trans orientation, because the allyl alcohol formed is basically the trans allyl alcohol. So that is the reason we can easily identify between the two combinations, only one combination has the allylic alcohol in the trans orientation, other one has the hydroxyl here. So in other words, that is the cis orientation. So the cis orientation does not take place in the case of selenium dioxide mediated oxidation. So we can easily identify what is going to be the final product in this second case. So let us move on to the next problem. So here again the major product A and B formed in the following reaction sequence are this is nothing but a beta keto ester. The beta keto ester undergoes a reaction, alkylation reaction using an alkyl halide in the presence of a base. Sodium ethoxide is used as a base that gives a intermediate A, and this intermediate A is further treated with the tertiary butyl nitrite in the presence of sodium ethoxide, and it is hydrolyzed. Then finally it is reduced with the zinc and HCl to give a product B. So these are all the various reactions that are being carried out on A to get the product B. This question was asked in December 2015. So let us look at what are all the possible things which we can actually rule out. Based on that, we have to now focus on only one or two options for the final product. The first one is basically the reaction, it's a beta keto ester. There is a alkylation reaction that is happening. So that means we have to look for the alkylation. If you look at A, in all the cases, the alkylation is actually happening. In one case, the alkylation happens in the methylene carbon. In the other case, the alkylation happens in the methyl carbon. So these are all the two differences that are given here. And if you look at option 2 and 4, basically the alkylation at the methyl carbon is not that facile compared to the one that is happening at the methylene carbon. So what we can say is the 2 and 4 are not the probable product that will be formed. Now we are end up with only two combinations, either 1 or 3 is going to be the final product, because both of them have the alkylation happening on the methylene carbon. So here in both the cases. So then we have to move on to the next one. The next one is the final product. So we finally have a zinc and HCl reduction. If you look at zinc and HCl reduction, that reduces many groups. So if that reduction happens, then we may not be having this nitroso group that is present in the final product, because that may be getting converted to some other group. So most probably an amine as the final product could be the probable one. So we can look at maybe 3 is going to be the product. So this is without looking at the reaction mechanism. We are just trying to guess what could be the probable things possible. And if we look at the mechanism, that will confirm whether what we have identified as the right product is the right one or not. So let us look at the individual reactions. As I mentioned here, we have a sodium ethoxide is used as a base. That base will abstract the most acidic hydrogen, that is the methylenic hydrogen that is present will be the most acidic hydrogen that will be abstracted by the base. That leads to the formation of a anion. So this anion generally exists in the form of a enolate, because we have a negative charge. So this will shift here and this will go here. So we may end up with a enolate anion that is formed. Since the enolate anions are stable species, this formation of the carbon anion is very facile. So then this anion attacks the undergoes an SN2 attack on the alkyl bromide. So the bromide group is lost with the concomitant formation of the CC bond that is formed here. So this is how the alkylation actually takes place in the methylene carbon. So in the next step, one more sodium ethoxide, one more equivalent of sodium ethoxide is involved. So that again abstracts the another most acidic hydrogen atom that ends up with the carbon ion formation. So this carbon ion can exist again as an enolate formation. So because of the higher stability, this anion is formed very quickly, and this now attacks our tertiary butyl nitride. So the tertiary butyl nitride's nitrogen is the one which is electrophilic in nature, because oxygen actually pulls the electron towards itself. So the nitrogen becomes delta positive. So this is the electrophilic site, and we have a carbon ion which is the nucleophilic site. So the nucleophile attacks the electrophile to form the bond. The carbon nitrogen bond is formed here. So here in this particular case, the tertiary butoxide group is lost, because that when it attacks, the nitrogen's valency increases. So one of the group has to be gone. So that is the reason that tertiary butoxide group is lost. And in the next step, what happens is like the liberated tertiary butoxide group now attacks the electrophilic carbonyl carbon. So this is how the reaction actually proceeds. So the liberated tertiary butoxide attacks the electrophilic carbonyl carbon, and during this process, the carbon-carbon bond is actually broken
from the tetrahedral intermediate.
So we end up with a couple of products. Loss of tertiary butoxide is basically lost as the tertiary butyl ester with the concomitant formation of the carbon ion. So that is the one that is actually formed. And since the oxygen is electronegative, it pulls a pi electron towards itself, making the negative charge from the carbon ion shift between carbon and nitrogen. We end up with the oxime that is formed in this reaction. So a proton transfer leads to the final oxime. The negative charge on the oxygen is neutralized to give the hydroxy group there. Then finally, zinc and HCl reduction leads to the formation of the amine unit. So that's how we can say the C alkylation, that is the methylenic alkylation, is the first step, that is the intermediate A, and finally the reduced nitro, the amino group is the final product, is the product B. So that way we can easily find it out. Our earlier option of identifying the product is actually explained through the mechanism.